Hi all, this is the first video of two on doing calculations involving the equilibrium constant, or Kc. One thing to watch out for in any question is that when you're using numbers, they have to represent the molar concentrations when the reaction is at equilibrium. So you have to check the question carefully to see what unit the substances are in, to make sure it's a molar, i.e. moles per litre concentration, and the reaction is at equilibrium. By the way, the second video will be how to do calculations when it's not at equilibrium. Remember how to calculate molar concentration. If you're given moles, divide those by the litres, like the volume in litres. Okay, the first one we're going to do is a simple calculation. Here's a question. I want you to pause the video and write down the question, noting in particular the units. So we've got a 3 litre vessel and we've got moles of those two substances. And the question is to calculate the Kc at the reaction at the temperature given. The first step to do is to write down the Kc expression that we did yesterday. So in this case it's nitrogen oxide squared divided by the concentration of dinitrogen tetroxide. You then substitute in numbers, but remembering the numbers have to be molar concentration, so you'd have to divide those number of moles by 3, so you get those concentrations given. Substitute them into the calculation and you get 0.694 molar. Remember to put the units in for Kc as we did yesterday, so in this case it would be molar, or just capital M. Keep the number in your calculator is my other suggestion. Don't round off to 0.167 squared. Keep that one in because it's actually 0.16 reoccurring. Another type of calculation to do is, given the Kc and most of the molar concentrations, calculate the equilibrium concentration of one of the substances. So again, I want you to pause the video and write down this question, noting this one has given you a Kc value and a temperature. First step always is to write down the Kc expression. Now you have to rearrange this to solve for the concentration of nitrogen dioxide. If you rearrange it, it turns out to be the square root of Kc value times the concentration of dinitrogen tetroxide. If you put those numbers in, you wind up with 0.17 molar. Be careful, as I've underlined in the question above, it's not now moles, it's now capital M, which is moles per litre. So check each question really carefully for the units for each substance. You've all been asking me about this QC versus Kc stuff, and I said I'd do it in the video today, and it's how do you know if a reaction's at equilibrium? There's a particular thing called a reaction quotient, or QC. You'll also see it as concentration fraction. That's calculated exactly the same as K. It's just at any time other than at equilibrium. Kc is only the constant when the reaction's at equilibrium. The reaction quotient is at any other time, but it is calculated exactly the same. So if you know the concentration of each substance in the reaction, you calculate Q and then compare this to the published Kc value at that temperature. Don't forget K is temperature dependent, so it all has to be at that temperature. If the two values are the same as each other, the reaction is at equilibrium. If QC is less than Kc, the reaction isn't at equilibrium, number one. Don't forget, both of these are products divided by reactants. So if Q is too small, there's not enough product. So in order to increase QC, there needs to be more product and less reactant, i.e. the reaction is reached via a net forward reaction. We're going to use that term quite a lot moving forward. What do we mean by net forward reaction? The rate of the forward reaction is greater than that of the backward reaction. So overall, the reaction's moving forward, i.e. making products, and the reactants are disappearing. So therefore the concentration of products would go up and the concentration of reactants would go down. So the reaction quotient value would increase up to K. This is done when reactants were put into an empty vessel and not enough time has passed to reach equilibrium. However, if the reaction quotient value is too large, i.e. it's larger than Kc, there's not enough reactant. Now that seems strange. How can you have not enough reactant? What it is, it's the person has put the product into an empty vessel and not enough time has passed for them to turn into reactants. So not enough time has passed to reach equilibrium via a net backward reaction, i.e. the backward reaction needs to go faster than the forward one. When would that happen? When you put products into an empty container. So the concentration of products is very high. The rate of the backward reaction is high. Not much reactant has formed. So the concentration of reactants is lower. Frequency of collisions between reactant particles is lower. So the forward reaction rate is lower. Hence there would be a net backward reaction required to reduce the reaction quotient value down to the equilibrium constant. What I want you to do now is to draw this axis for a graph. Note on the left-hand side we have molar concentration between 0 and 5 and time in minutes on the x-axis. Then I want you to go and put these two lines in. The one labelled R is the concentration of reactants over time. They start high and then go down to 1 molar by 12 minutes and then that concentration remains constant. The products concentration would start at 0 and then go up to 5 molar by the 12 minutes and then those concentrations would remain constant. Note, if you look at this graph, because the reactant and product lines have become parallel at 12 minutes, it means the reaction has reached equilibrium at 12 minutes, i.e. the concentration on reactants and products are no longer changing, so it's reached dynamic equilibrium. On this graph, at the 5-minute mark, the concentration of reactants is 2 molar and the concentration of products is 3 molar. The question is to show that this reaction is not at equilibrium at 5 minutes. Calculate the QC at 5 minutes, which is always products divided by reactants, i.e. 3 divided by 2, which is 1.5. Then you do it again at 12 minutes. Products is 5, reactants it's 1, no it's 5. So those two values are not the same as each other, so it's not at equilibrium. As the reaction quotient is less than Kc at 5 minutes, the reaction would be reached via a net forward reaction. Another question for you, I want you to write down. This is a longer one. This is a multiple part one. So I'll just get you to pause the video and write down this question. part A is to calculate the Kc at 250 degrees. So I want you to pause the video and calculate that, then come back and check the answers, paying attention to the units for all substances. Right, step 1 is to write down the K expression, noting it would be molar. As you've been given moles, not molar, and a volume for the container, you need to calculate the molar concentration by moles divided by volume. So divide all those moles by 3 and you get those answers there. Substitute them into the K expression and you get 0.4 molar. The next page will have part B. Part B is some different number of moles, and you need to show that this is not at equilibrium, i.e. this is a QC versus KC question. So I want you to pause the video and have a go at this one on your own, and then come back and check the answers. So first of all, write down the expression for QC. Note it's exactly the same as KC. Because you've been given moles and a volume, calculate molar concentration by dividing them all by 2 this time, so you get those concentrations there. Substitute them into the reaction, you get 0.416. Now as 0.416 isn't 0.4, i.e. QC is not the same as KC, the reaction is not at equilibrium. Next part of the question, in which direction would this reaction reach equilibrium? What a question like that means is it via a net forward or a net backward reaction? So you would need to state, in order to decrease the reaction quotient, because it's too high, the concentration of products would need to decrease and the concentration of reactants would need to increase via a net backward reaction. Part C is over the page. Part C, another equilibrium mixture, note that term there, contains this molar concentration of those two substances at 250 degrees. I've underlined the important bits there because this is going to help you, because it said what's the concentration of chlorine in this mixture. Note if you just glance at this question, no Kc value has been given, but because you've been given the temperature and you've been told it's at equilibrium, you need to go back to part A because you had to calculate Kc at 250 degrees. So if you write out the expression for Kc, you've already calculated it in part A that it's 0.4 molar. Now rearrange the equation to solve for the concentration of chlorine, and it's as above. Substitute in the numbers. Note these are molar concentrations, so you don't need to divide them by any volumes. Substitute your answer for part A and you get 0.8 molar to two significant figures. Part D, determine the Kc for the following reaction at 250 degrees. So what you have to do is compare this reaction to the one you've already done. So the equation we've been writing a lot, this one is reversed and all the coefficients have doubled. So the new Kc value is the reciprocal of the squared value of the old Kc, i.e. 0.4, remember? And it's 0.625. Note the change in units, so you have to be really careful of the units. Thank you. This is the end of this video.